Woof. Woof. Aha! Alright, now they can hear you.
All right. So I guess I'll share my screen, but like they don't need to see it, I guess. Just
Okay.
like in case you want to see anything. So I'll go into the workspace that we've done.
Oh yeah.
And so something I like about this is that so sometimes you need to up the stakes and do the stuff in public. So I do like to do that a little bit. Anyways, quantum. Let's just do a note called quantum, and so something is that I probably will want to give you some links, and then you might try to click on it. Okay.
Yeah, no, that's fine.
Okay. So currently I'm in the quantum notes. If you want to join that.
Yep.
So you should see my cursor.
Yep, I can see your cursor.
All right, that's cool.
There.
So there's different like subfield in the quantum computing. One that will be of interest to you, then it will be quantum machine learning. The thing is that how can I say this? One of my field of research is actually the quantization. So what this means is that like you take a quantum circuit, you take a quantum system, and you try to make it run as fast or even better than on a quantum computer. And actually something funny is that like a lot of quantum machine learning algorithm are in fact dequantizable. So that's something to keep in mind. But maybe, okay. So there's a lot of different way we can start, but something I like to do is like just make people go on IBM Composer. So let me give you the link. So this should be the link here.
Yep.
Oops, this is. So once you're on it, tell me.
Where did you send it?
Yes, I sent it. In the affine, in the notes.
Oh, gotcha. All right. I'm in.
So now you should see like some kind of weird sphere with like some blue bar on the left, right?
Yes.
So okay, so this is a bit weird to describe, but I guess you can look at my screen and then maybe do it. So the first thing is to understand that like you when we do quantum computing, you end up doing a bunch of like gate operation on some circuits. So one of the operation we'll just flip a bit for now. So there's this X operator that all it does is if the qubit is at 0, it will put it at 1. And if it's at 1, it will be at 0. So this is the X operator, also denoted as like the plus here. You see that?
Yep.
Hell yeah. All right. The other thing is that like in this realm right now, it's kind of like classical Boolean. Are you familiar? I don't know how familiar are you with like Boolean stuff and stuff like that.
Not too familiar.
Okay, so let's go into the notes really quickly. So if I show you, let's say a target table, A1, A2.
Yeah, when it comes to quantum computing and stuff like that, I have no idea.
Yeah, that's totally fine. Also, for me, it's like kind of a test run to see how this go. I think it's quite the time to be like, oh yeah, I'm doing some research in quantum computing, and to be like, oh yeah, here's this VTuber. Let's try to do something, anything. I think that's cool. Anyways, so Let's say, okay, so in classical computing, there's like these weird gates. So this will be an AND gate,
Yeah.
and then you have stuff like the OR gate. I think it's like this, and then you have like the XOR gate. Also, I'm kind of surprised that like I think Affine is quite good right now because even though you're quite far away from me, like it seemed to be like working really well. That's good.
Yeah, it seems to be syncing up quite nicely.
Yeah, that's great. Okay, so something to know is that like in classical computing, all your operation are like made up of all of these gates. And with and there's one gate that I should do. I think it's like this. This is the NOT gate. So what this does, so let's start with the NOT gate. So the NOT gate, what it will do is that if you start with the state 1, it will give you a 0. And if you start with 0, it will give you 1. That's clear, right?
Okay. Yes.
And so you have also this gate, like if you have the OR gate, for example, it's if one of them is 1, then the output is 1. So if either one of the output is 1, you have 1. And if we were to represent that on the truth table, this is called a truth table.
Yeah.
Then you would get 0, 1, 1, 1. And are you able to describe in your own words what I just did?
No, because I don't know where the other one come from.
Ah, okay. So, right. Okay, a good question. That was actually, yeah, I forgot to mention. This is A1, this is A2. So these represent, so these are the input.
Yeah.
I forgot that. And this, well, this thing, the X, is the output. And so the input here, it can be either 0, 0, 0, 1, 1, 0, or 1, 1. And so the corresponding, and so the output can be either 0 or 1. But here, what we do is that for each possible state, we list if it's either 0 or 1. Also, I'm assuming there is something. How familiar are you with binary, actually, in general?
I know binary. I just don't know it off the top of my head. Okay. But I do know how it works.
Okay. So you have a general idea. Okay, we won't do like binary arithmetics, but it's just that like we will be talking about qubits. So like we do start getting weird with that. So, anyways. So we have these gates. So the thing to understand is that like these gates have different truth tables, and because of that, you can do a bunch of arithmetics. So as soon as you have the plus and the minus, you can basically do all the operation. And there's a way to do that with something. Oh, okay, maybe I don't know if I'll go there, but there's something called an AND gate, and technically you can do everything with this single gate. You can compute anything with just like chaining a bunch of them. So when I say chaining, you will have like another one like this. And this principle of like a set of gates that allow you to do every computation that you need, there's also this equivalent in quantum that we'll call universal gate set, but this is a subject on its own, but whatever.
Yeah.
Okay, so the thing is that like I don't want it to be, I really want it to be a learning experience for you. I don't want you to be just confused. So so is everything okay right now?
Yes. That nano gate, can that?
Yes.
Or technically all the gates.
It's NAND.
Oh, the Z.
Yeah, sorry. Yeah.
So can they all, like, how you currently have it, can it all be connected? Like, are they all connected, or?
Oh no, so something, okay, so let's say you wanted to do like, okay, I'll give you like okay, so this is just like two gates. It's connected to nothing right now. So it's just like two gates in the void, drifting away alone
Yeah.
and depressed. Uh, but if we wanted, let's say, to reproduce the not gate with this, what we would do is, like, you would only need to connect the two input. So why do we need to connect the two input? Because this is an AND gate again, but what does it mean to be an AND gate? I'll put the truth table. No, I should do just streamline. A1, A2, X.
Maybe a quick refresher on what the ones and zeros do in classical computing?
Yes. So, yeah, so the thing is that in like, oh my god, okay, there's a lot to talk about. Okay. We'll see how far we get. We'll see how far we get. Okay. So let's say you have an instruction like I don't know. So this is the binary string. This is just to indicate that this is binary. This is just to say this number is a binary number. You need to do that because you could store a bunch of 0 and 1s, like and you need to know like what these represent. But in programming, the thing is that like when you program something, you end up like you could write 10 or you could write 1 0. How do you know which one you just wrote? You put a 0b before. So that's why there's a 0b. It's to be able to tell, oh, this is binary. This is not like just 10, or like this is not like a comically large number or something. So what binary does is that like you have like these chips, right? Like let's say a CPU.
Yeah.
And this thing will like coordinate with like some memory or something. But to do so, like it needs some kind of logic or some kind of instruction. So let's put like some instruction register or something. It will usually be in the CPU, but whatever. Register, my box is too small. So what you do is that like you basically send like one of these binary numbers. Then you have circuits, like you have circuits that are actually very similar to like the gates I showed you. Like internally, you have something called circuit that are like VLS. Why am I using this acronym? Nobody knows what that is. What we have is that like we have like the inside of like each of these chips are like cooked. Like there's physical circuit like that will be if you okay let's get. Do you know what a wafer is? Let me pull you an image. I think it will work enough fine. Let's try it. Yep, there we go.
Okay, I've seen that. I just don't know what it is.
Yes. So what this does basically is that like it's a way to you have like these transistor circuit with like some resistor or whatever. Okay, let's not go. Oh my god, okay, I'm just realizing that I'm building a computer from scratch right now. Okay, that was not my goal, but it is what it is. Okay. So you have these transistors. This is probably the wrong symbol. I forgot the transistor symbol or whatever. And if you chain them, you can make, let's say, the AND gate. So we'll just focus on the NAND gate. Also, the NAND gate is the same thing as the AND gate, but inverted. Also, I did not finish my... Okay, let me just take a... Okay, let's just at least say what is an AND gate. Okay, so this is 0 0 0 1 1 0 1 1. So this will be 0 0 0 1. So basically, it's only one. Is that right? No, that's not right. That's 1 1 1 0. It will be only one when it's not 1 1. So yeah. So if there's a one here and a one here, then it flips the result. So right now I say it's 0, but yeah. Am I missing something? Am I missing something? No, I think that's fine. Okay. So go back to the wafer. So these wafer basically have a bunch of like transistor. Okay. These transistors make a bunch of these gates. These gates make a bunch of logic. So let's say you want to be able to parse my binary string. You want to be able to parse this. Parse binary. Well, you would basically make some weird contraption of these gates.
Yeah.
And suddenly you would be able to like process some information. And so these wafer, all they do is like encode a bunch of these gates inside like a chip, something physical. So when I say cooked, it's like kind of basically that. It's actually like cooked within the chip. So we just put all the gates within it, and all the chips within like a small section of this wafer. So oh yeah, and just to be clear, let's say this is a wafer. Each section is like for a different chip, or can be for the same chip, but like it's like to make the same, either to make the same. Okay, we'll just say it's to make like the same chip. So this one maybe is able to make like, I don't know, like 1,000 chips. Let's say this wafer is like maybe 1,000 chips that it can make.
Yeah.
So okay. So well, okay. All of this say this wafer, this logic unit is how you make something like a CPU. Is how you make memories. Albeit like there's like some in the case of memory, you have like some physical stuff that you need to do on the wafer for it to be able to store stuff. And then you have instruction register. And now you have your binary string. And what you do is you send your binary string to your instruction register. And then you say, let's say, oh, this instruction is actually to get memory to send me like a cat picture on my computer or something like that.
Yeah.
I cannot draw a cat, so yeah. Well, yeah, no, I did. Yeah, no, this is a disaster. Whatever. I'll just write cat. Okay. So the binary. So basically, this is binary can only be 0 or 1, and then you can use these to send instruction or to store stuff in memory. So in a PNG file, for example, it's basically just a big array, a big like sequence of number of binary. And so I don't remember exactly the PNG format, but like it should be something like, let's say, I'll just make up some stuff, but like the general idea is that. So maybe these 4 will represent the color red. Maybe these 4 will represent the color blue, and maybe these 4 will represent the color green. So you can kind of like, and then it's like, how do you know that it mean red, blue, or green? You cannot just decide it. You just decide that it's red, green, or blue. And so all of this say, I think this gives a sense on how binary is used. Would you agree?
Yes.
Okay. Do you think something needs more explanation, or?
Canberra did say, so transistors turn on and off to represent 1 and 0, and a bunch of Transistors in a chip perform a particular function we call logic gates. Is that about right?
Yes,
Yes.
albeit there's some precision about transistors. Actually, you can see them more as gates, let's say you have a dam and you want to let the water flow. You can just like lift the gate a little bit to let some water or more water flow. So it's actually not a straight 0 or 1 in the transistor, and so that's why you have to do like some circuit shenanigan to actually make it so that like it's either 0 or 1. So this is something that like actually the first time I learned about how transistors work in circuit and everything, I was quite confused because I thought it was only 0 or 1 like a switch like you see, but it's only one of the application of transistor. You can also use it to amplify signal and stuff like that. It's like a really weird nonlinear creature, but basically yes, basically what the person said is right. Okay. So where are we going with this? So I guess, okay, so we have like these gates, we have a new universal gate set.
So a combination.
Okay,
of
this is all.
transistors. So a combination of
this is-
transistors is needed for a clear 0 or 1.
The accommodation? Sorry, I did not hear that.
So a combination of transistors is needed for a clear 1 or 0.
Yes, basically.
Okay. Oh, can you see chat as well? you want
I've
that?
not opened your stream actually. I should probably do that. Is it on like your Twitch?
Yeah.
Okay. Oh yeah, it just your Twitch link I think is like out of date.
Oh,
On the notification when I click on it, I see like no channel.
is it? I
There
did
you
just
go.
send it to you.
Okay, okay, this one is good. No, it's just on the Discord. You send the Lunako OG.
Oh,
But
it
this
is
one good. No,
outdated.
it's just on the Discord. Okay.
Thank you for
Okay,
the heads up.
okay. Now I can see the chat and get bullied by your chat. That's yeah. So I'm sure you probably have a pretty nice community actually. So I'm not too worried about that. Okay. Anyway, so all of this just to describe that like this is like the logic gate is how we do operation in the binary land. So now I guess we'll enter the quantum world here. Quantum just below. So the way it works is that like we, instead of like these binary thing, we have like these primitive that are like, so right now in quantum computing, we're in a state where instead of like just running some high level program, you literally just put like it's like you put the logic gate directly into the machine. It's like a level below assembly in some sense. You don't write assembly in quantum computing. You basically you would be able to define assembly in the way you do your quantum circuit. Don't know if that sentence made sense, but anyways.
No.
My bad. So anyways, so you have these sets of gates, okay? And so if we go onto IBM Composer, this is like the way I prefer to start with it. So on IBM Composer, there's all of these gates. These are primitive operations. So if you put like the plus, this is just like the NOT gate in classical. So all it does is that if you are in 1, it will flip to 0, and if you are to 0, it will flip to 1. So you can try just dragging like the plus gate. So it's like so the notation is a bit weird in quantum computing. Some people put the X gate, some people put the plus. It depends on whether or not you want to be annoying. So IBM want to be annoying, so they put the plus. So you can drag these gates. But then if you want to get really interesting, you have these gates named Hadamard gates. What they do is that they put your qubit in superposition. So let's say, so I guess how can, okay, I want to make it interesting for your stream, but I think only you can see my stream, right? So
Yes, at the moment.
yeah,
I'm
so
slowly
that's fine.
copying what you're doing.
So, okay, you're just copying. Okay, that's good. So right now, if you look at like the state 0 and the state 1, when you measure the gate, you will have like a 50% chance of either measuring 0 or either measuring 1. And you can represent that with like the measure operation, but it's like you won't say anything because it will do the probability. So now if you put the measure gate, you'll see that like it gives you like some simulated probability of you getting 1 and 0. And where I want to go with this is that one of the important thing to understand is that when you work with a quantum computer, there's this thing called the state vector that we'll talk about again. And each time you measure the quantum computer, you collapse the state vector into a singular state. And so if we were to add like, let's say, another gate here, and let's just make it, let's put like some weird Rx and, oh yeah, okay, so I'll go slow for you. So let's put 2 Hadamard gate, then let's put an Rx gate on the second qubit.
Wait, hold up. Wait.
Well, sorry.
How'd you remove your things?
Let me look. Oh, so what I did is that you can click on the qubit on the left, and then you can press on the trash icon.
Oh, gotcha.
And yeah.
Okay. You got 2 of those.
Yeah, now
Okay.
I got 2 of those. And so maybe just to be annoying, we'll put 3 actually. Let's put 3. So we'll do this. This is an untangling gate. We'll come back to that. And then we'll put a Rx. And then we'll edit the Rx so that it's like pi over, let's say. No, what am I saying? It's not, Rx won't work. It's R1.
Wait, how'd you add another line?
Oh, you click on the plus. Like you click on the qubit and then the plus. Add a qubit after. Like on the left zone here.
Oh, okay. Okay. Okay.
All right. So let's put a RY gate and let's put let's say pi over, I don't know, I'm vibing pi over 8. Okay. So now you should have a circuit that, yeah, okay, that's good. I'm looking at your stream. Okay. And so, like, I do have like a CNOT gate, but we don't really need that, honestly. Like, it's a bit confusing. Let's remove it for now. So now, if you look at the probability distribution, you have something that's not like even. It's not like the same thing. And the thing to know is that, like, when you work with a quantum computer, each time you want to get something out of it, you have to measure the state vector. And when you measure it, you get a single result. And you will get that single result like a probability % of time. So what this really means is that, let's say you run you will run the same quantum circuit, let's say 1,000 times, and then you do probabilities on that, and then you get the graph on the lower left. Does that make sense?
Yes.
And so that's the thing to remember. There's a step. And that's why, like, there's a bunch of quantum algorithms that actually are not that good, or like it's hard to prove that a quantum computer will be useful because the decoding step need to be really smart. If your probability distribution is like within 20 qubit, to give you an idea, let's go back to affine. For 20 qubit, you have 2 to the 20 result that you can get. The thing is that if it's evenly or almost evenly distributed among distribution, it become to be it's really hard to find like the optimal result. So 2 to the 20 is actually quite doable for normal quantum for normal quantum computer. But there's application where we'll need about 2000 qubit, and then we get like a crazy huge number. Like I cannot write it. It's like, let's say 1.6 times 10 to the 60. It's comically high. So this, okay. So maybe maybe I need to be a bit more clear right now what I'm saying. So you have these circuits. You want to sample them. Then the if you have 1 qubit, you have 2 to the 1 outputs possible. If you have 10 qubit, you have 2 to the 10 output possible. And if you have 20 qubit, you have 2 to the 20, and so on. And you can see that it's the number of output scale in a insane way. And the thing is that it both gives you power to compute everything, but also the thing that like the media doesn't talk. If we put our tinfoil hat, we don't know why they don't talk about this, but it's because while you can solve in this big solution space, the output also will have the probability of giving each of these. So it can give you, so okay, how can it, if you were to do just like an Hadamard circuit, like just a bunch of Hadamard, then all of your output are equally as likely. So you need to find a way to collapse them, to collapse like the probability distribution into like some smart peak or some sort of encoding that you can decode in some reasonable amount of time. You don't want to be running the circuit 20,000 times. So in quantum computing, you end up working with something we call this oracle. But I think I'm jumping a little bit too much ahead right now. Okay. Comments. Do you have any comments? Any?
No.
Let me read the chat. So I need you know. Yes. So anything you do, you often need to do a huge number of measurements. So in papers, you actually see in the complexity analysis, you see the number of sample you need to sample your quantum circuit to get something. Okay, and then okay. And I have a lot of interesting things to say about that, but let's go into the like this gate right here. Okay, let's just describe like some behavior of the gate. So we'll do something we called a Bell state. So maybe you have heard of quantum teleportation. Did you hear of quantum teleportation? Like vaguely, like oh, some physicists teleported to molecule or something.
I think so.
So the thing is that like it's kind of a it's kind of a physicist thing, because for them teleportation just mean if you have like some quantum object and then you reproduce the quantum object state onto something else, you basically have teleported the state. But it's not like actually it's not like actually teleported. It's more like you have teleported information, but whatever. Anyways, okay. What I want to introduce anyways is just like this gate right here. So this is an entangling gate. So this is the spooky action at a distance that you might have heard about. So entangling, what it means, when you entangle 2 qubit, it means that it is statistically correlated. So what this means is that a change here will statistically affect the result here. So usually in the media they'll more say something like they won't say it's statistically correlated. They'll say like if the spin is up, then you know the spin of the other thing is down. in like some quantum object, in quantum spin object or whatever. Statistically correlated here is more. The reason we use that is that if something happened here, you can make it so that like it change the probability of the output only slightly here. And so if we go to IBM Composer, let's play with that. So would a quantum computer still be faster than classical? Haha. So that's the thing, is that right now the usual quantum computer can go to about so it depends on the circuit, but like for a superconducting quantum computer, we're talking about like the public number would be 5,000 hertz. So it means you can execute 5,000 like circuit per second. The thing is that like it's like something like 10,000 times slower than a quantum computer, than a classical okay, sorry. So right now, if you go by the number of time you can execute a circuit, it's like 10 million times slower than a classical computer, or something ridiculous like that. But the interesting thing about the quantum computer is that like the algorithmic complexity is much lower. So the number of operation that you need to do is much lower. But that's why like people will say it's not faster, because it cannot run a lot of circuit compared to like a classical computer. Actually, something funny is that you can simulate quantum computers very easily on your own laptop up to like 30 qubit or something. And then if you, something that a lot of physicists don't know about is that you can actually go to like, I can run like 150 qubit on my lap. Okay, I can run circuit that go to 150 qubits on my laptop. They just have to be very specific quantum circuit, and you just have to use a simulator that's not that's made for that. So this is like, I don't know how far we'll get into this, but like also Lunako, how do you know any coding at all actually?
Any coding?
Yeah, like Python or C++, C, or
Yeah.
anything.
Yeah.
You do? Okay, that's great.
Yeah.
So what's your, I don't know. I feel like I want to know more. So how would you qualify your ability to use this language?
I know Python quite well.
Okay, that's good. So the thing and the cool thing is that in quantum computing, most of the libraries are actually basically, because you just define a bunch of gates and then you send it to a quantum computer, you just take a language that like is easy to use, like Python. And so most language actually in quantum computing actually works with Python. So I mean, I don't think we'll go there today, but okay, let's talk about the entangling gate first of all. So let's just do this circuit that I showed here. So now you have I'll let you recreate it. So yes.
Hold up.
I think your voice. Yeah. So sorry. I think your voice cut.
In theory.
Yes, in theory.
Would you be able to run an entire LLM on a quantum computer?
Actually, that's funny because we, in the quantum club that I'm part in also, that like lend me a bunch of research opportunity or whatever. We actually did there is quantum LLMs. You can do NLMs within a quantum computer, and there are papers describing how to do that, actually. there's a lot of interesting application in quantum computing. And so this is another part I wanted to touch onto today, is like all the cool project you can actually do that like you don't hear at all about in the media.
Okay.
So yes, you can definitely do that. Just before that, I just want to finish the. Okay, so I just want to present like the entangling gate, the
Yeah.
2-qubit gate, and then we can move on to like a cool application.
Okay.
So just to say, so this is like a CNOT. This is an Hadamard gate.
Yep.
And so the Hadamard gate, if you remember, it had 50% chance of like going to 1 or 0.
Yes.
And the entangling gate here, what it does is that if the first qubit is at 1, then it will flip the second qubit at 1. If the first qubit is at 0, then it will flip. It won't flip anything. So the second qubit will not be affected. And the thing is that like this circuit looks simple and everything, but you can do if you do something like it's here. I think you'll see it here actually. Yeah, okay. Do I need to do something fancier? Should what am I? Okay, well, whatever. Oh yeah, okay, there it is. There. Why was I confused? So if you go and just put like the circuit I just put,
Yep.
because right now it might seem like it's just a probabilistic circuit or whatever. There's like I could do like a mini course on why it's not actually like normal probabilities, but I won't do that. I don't think it's. I think there's cooler stuff to talk about. If you do like a circuit like that, something you'll notice is that like on the right side, lower right, you now have like some new colors, and so this is to represent like you have like this phase in your quantum circuit, and you have like these relative phase. So I'm not sure how familiar people are with phase, but basically you have like some mathematical object that like shift depending on what you put, and that's a key part of quantum computing and quantum algorithm is exploiting these 2-qubit gates and these phase changes. And if you do that, you can create like that's how you create like algorithms that are valid. So just to go to I find something I like to do is that it just to say that like if you want your capacity, because something you can do is just like make anything on a quantum computer and it's like useless or whatever. But if you like, it might be reproducible on a classical computer. But if you have superposition, so if you test multiple state at the same time, in some sense, if you have entanglement, so this is 2-qubit gate. And your algorithm exploit something called phase kickback. So this is what we have just seen. The circuit I showed you is an example of phase kickback. Then you might have something useful. If your algorithm does something useful and use all of these 3 properties, then maybe it does something. Then maybe it's useful. Like this is like. This maybe it computes something that like you cannot easily do on a classical computer. So the physicist won't tell you like that there's any way actually to know whether or not something will be useful. But just working with quantum computer, I think to me it's obvious that like if like some calculation don't incorporate these 3 elements at least, like you will not get like some asymptotic speed up. All the good algorithm exploit these 3 properties. And yeah, okay. Okay, so question, comments, maybe insults, I don't know.
So with are there more what do you call them? More elements or whatever you called them? The ones on the left-hand side? Or is it only these 3?
So So let's say computing requirement, like a requirement for useful, let's say requirement. So in quantum computing, oh yeah, that's the other thing, is that in quantum computing, you don't actually have a lot of quantum effect that you need to know about. It's if you make the hardware, if you do quantum sensing, if you do quantum communication, that you'll need to have more of these effects. So another effect I guess you could have is like the decoding, like it need to have like something, I'll say like sparse decoding and reasonable encoding. So reason. Okay, I forgot how to write. I don't know. Whatever. um, um, yeah. So you need to make it so that like the distribution that you get is easily decodable. So something I like to show actually is like, okay, but how do you do anything with a quantum computer, right? Like, what do we even mean? Like, what do you mean you have these gates and like they do some weird stuff with like probability and stuff like that, you know? So, um, okay, so this is like, I don't know if you know any of this. Do you know about like the Fourier transform?
No.
Right. So, there's this algorithm that like you can have like these wave thing. Like you, let's say you have like this wave right here. Okay. This is the time. This is the amplitude. And if you do a Fourier transform, what it means is that like your signal become frequency. So maybe you're familiar with like something called an equalizer. So this become
Yes.
the frequency. This is
I
all,
know
let's
something
say
about
M.
that.
So equalizer, like in audio, is basically like I'll if you've seen like this, it's like kind of weird. Like why do you have like this signal like that, and then you, on the equalizer you can always like you see like a bunch of spike everywhere, like on the whole spectrum, I guess. Um, and the way to get your sound from like a single wave into this form is with a Fourier transform. So basically, all it does, like, yeah, the thing is that like you can spend a lot of time on this. So uh, I'll try my best. I'll try my best. Okay. So Fourier transform, basically, it takes like some sound or some signal or whatever, and then it will put it into the frequency domain. All it means is that the x-axis on your graph will be the frequency. Or another way to say it is that like currently you have this signal, and then you can see that like your signal is at 60 hertz. So I don't know how much we know about hertz over here, but it's just the frequency. It just like we know that at this frequency there's some signal. So this is a Fourier transform. So question, comments.
Cambrai has
Uh,
one.
let
When
me
you
see. Let me
say
see.
incorporate these elements, what is it? What does it mean to
So
have?
okay, yep. So to have these elements incorporated, what it means is that ultimately you need to have a 2-qubit gate. You need to have an Adamo gate, and you need to construct your circuit such that the distribution output is like smarter than like just all the probability, all the output possible. Um, and yeah, and if it's not within, if your algorithm doesn't have that, you probably don't have something useful. So this is what I mean. So, okay. So why am I going into the Fourier transform actually? Okay. So, okay, maybe we don't need to understand exactly what it does, but what we need to understand is that like there's these quantum version of these algorithm that will literally be called quantum Fourier transform. Okay. And you can just put like these block on whatever. Okay, so what I mean by that is you can encode some data on your quantum computer and then just apply the quantum Fourier transform and then just decode it. And that could be like the whole operation that you do.
Yeah.
So if I wanted to be annoying, which I guess I want to be right now, let's do a Fourier transform in IBM Composer right now.
Actually, now that we're back on here, Canberra asked, is there a gate designed for using each of the elements?
So usually, so the thing is that they're not specifically designed for that. It's just that like they do that, and most of them do that. So the Hadamard will put it into superposition, but then you have stuff like the RX gate that will also put it into superposition. But like if you want to do entanglement and have phase kickback, you need a 2-qubit gate. And the thing is that with 2-qubit gates, you need a 2-qubit gate to have phase kickback. That's it. And actually, okay, maybe we stop with the Fourier transform trolling a little bit and we go on the Pulsar Studio. Let's go on Pulsar Studio. So right now I've shown you like, so IBM is, okay, get started. I'll give you the link here. And so there's different way to have a quantum computers. One is with a superconducting circuit, but another one that's very interesting is with neutral atoms. And the thing is that depending on the underlying technology, you'll have a specific set of gates.
Hold up.
And
it's
yep.
telling me to sign in. Give me 2 seconds.
Okay. So I have cool examples that Lunako would be able to see, but on this system. But so basically, okay, I'll let you log in. I'll wait.
Boom. Roll. Bingo. Go back over here. Go back to this. All right, there we go. All right, I'm back. And I'm
all right. All right, that's good. So now you should see like a screen with like a bunch of like really confusing stuff. So
yes.
Let me see on your stream what it looks like. Okay, yeah, okay. So let's just go with the default. Let's just click on generate a pattern. So it just to play a little bit, just to give you an idea, is that like there's different way to do the entanglement mechanics if you go on the physical hardware level. So with IBM, they use I forgot the name of it, but like they have some superconducting specialized circuit that basically will act as the entanglement. In the neutral atoms, you have this something called the Rydberg blockade effect that goes on. The idea is that like if you select like one of these atoms,
yeah,
and just play with them, you'll see like a yellow, like a yellow circle, right? So this yellow circle, what it does is that it indicates you that like if that atom is like excited, then the other one near it cannot be excited. Or another way to see it like in a more common language would be if this atom is like set to 1, then the other one must be 0 because there's like some physical effect that block the atom. And so
okay.
And the thing is that like you can apply like some pulse onto these, and the pulse will correspond to like some gate operation, basically. I will have to talk about Hamiltonian and stuff like that, but like it gets very confusing very fast. I think we already are talking about all of that stuff really quickly. So maybe but I do like to show this because this is much more closer to what you actually they actually do on the neutral atom computer. Like they literally place like neutral atoms, and then in some smart way, then they just shoot a laser. Then it's like you got this state, easy. Um, and yeah, okay. And these operation, you can represent them with gates, like you've seen in quantum in IBM Composer. But it's just that like it's a bit like if you want to optimize your code, something you can do is go into assembly mode and then really like go into the gritty neat. Okay, sorry, I forgot. Rip English. Okay.
English.
You can go into the English is actually really hard. I still cannot do like the th sound properly and the r. Like I do a fake French r every time I say it. Whatever. Anyways, so you have these. If you want to go into more details, to optimize your program, you would use like literally how the quantum computer work to optimize the execution and to have less noise. That's the other thing is that like a lot of stuff actually, a lot of stuff actually, a lot of quantum operation are not optimal actually on real hardware. What they do is that they transpile, they take some set of operation and then they convert it into a set of operation that the quantum computer support. But anyways, okay, neutral atoms, IBM Composer, the QFT, which is on one qubit just an Adamar gate, which make me laugh. Where do we want to go with this? I guess we'll go with, let me, nitty gritty. Thank you. That was a term. Okay, so let's talk about the application, I guess. So I'll switch on my side on some stuff. Give me some moment. So far, is everything good? Is this fine? Are we?
Yeah.
Oh, okay. Okay. Let me just need to do BTS.
Can I just say I currently have him muted? I have me muted.
Why do you have two streams on
That's
YouTube?
that's how
That
you
one's
know.
for you.
That's how you know that he knows what he's talking about. That's how you know that he knows what he's talking about.
Oh, no.
Dude, this is blowing my mind. And you know, I have two streams on YouTube, one shorts and one big screen, because
Actually,
I think if people like interested in
the
like the
link, I cannot
shorts
just
part,
give you the PDF, so let me get the
then
link.
they could go to like the big screen, if you will. Also,
Okay,
if you
so-
don't want to get ads, that's probably a good place to go as well. It might be a little bit delayed,
something
though,
you can do is
but he doesn't have access to
that people
that stream.
that people don't know about is that you can actually do like you can do audio with quantum computer. You can render games if you wish with quantum computer. You can make exactly like an LLM with it. Like the thing is that like you can logically do everything that like a classical computer do, because you have like all these gates that basically do the classical, can reproduce the classical counterpart. The only thing is that you don't have memory on a quantum computer, and the way you measure it is very weird. So I guess I'll send you these links just to show on stream. And cool. So let's put this one here. This this one here, and this one here. So these are some of the false ones. Go. Is everything all right?
Yep. I was just in a
Okay.
the drawing thing.
Okay. Let's go with the remarching one. So we don't need like we won't go into the details, but it just there's different rendering method, and like this is an example. If you scroll just a little bit down, just to give you a vibe of the mathematical stuff required to understand this. By the way, if you want to learn the math to understand these kind of paper, like we can do that also. So yeah, you can render a scene in quantum computer. If you go, you can render it with remarching. You can render it with ray tracing, which is another link I sent you, the other link I sent you, and then you can represent it with audio. And something is, I don't know, maybe you would like to appreciate a bit of that, or like do some comment on that. I don't know. So on the audio one, something I find cool is that like it's like the perfect example on how you can uncode stuff. So this is not a very smart way, but if you go on page 13,
so
you'll see like
an entire game on a quantum computer.
Yes, you can. Well, you will have to have like some classical loop within it. But like you could render the whole game, and like the control could be like the like you could control the character movement with like changing the angles in the gates, and yeah, basically yes. It's just that like you would have you cannot do it entirely in the quantum computer right now, but like yes. Like this is there's some guy that I think did manage to do. Like a theoretical version of Doom on a quantum computer. But when you look into his quantum circuit, it takes a gigabyte of data just to run, and it's like no quantum computer can run this, but it can run on like some weird specific simulator. Because okay, there is another thing that if you have a specific set of gates, you can actually like classical computer actually are extremely good at simulating like these set of gates. Like you can go to millions of qubits without any issues, and you can compute them really fast. So there's, as soon as you add like some weird gates, that's when like the quantum computer need. That's when the quantum computer need could maybe be faster. But yeah. Also, if you're interested in like doing an LLM, maybe. I could brush up on like some of our quantum LLM stuff that we did, and maybe we could like try to do something.
Yeah, no, I'd be done. Would a how do you put this? Would a quantum computer playing a game, would that be better on a quantum computer or a?
Oh no, definitely not. Like it's like you're definitely better off doing it on a classical computer. Right, it's like the number of shots that you need and the price it will cost you. Like okay, I cannot go into details, but like if you want to run a quantum computer for like something like 13 hours or something, let's say on the IBM machine, it will cost you something like more than $60,000. So it's like, and you might be able to get like, I don't know, like right now I guess you would get something like I don't know, like maybe 20 to, like, I'm just guessing a number, but you would not get like a 30 FPS experience, let's say. Yeah, it will. And but there's a question though of like, is there an algorithm in there in the gaming stuff that like could be faster with a quantum computer? And actually there are theoretical stuff that might be faster. it's like it's like weird stuff. Like there's like this Z buffering algorithm in like classical computing that nobody uses because it's not efficient. But on a quantum computer, it's actually like quite nice to do.
Yeah.
But the thing is that like encoding the states is like very not nice to do for it to work. So there's a lot of these kind of things. But yeah.
Interesting.
So yeah, on page 13, the thing I wanted to show you is that like you basically have the example of like how you can encode like some data in a quantum computer. This is like it's not the smartest way of encoding audio, but it is a way. So what you can do is you can encode the waveform of your audio directly into the probabilities of your output distribution. And then when you sample it, you to reconstruct it, well, you have the probabilities after, let's say, 10,000 shot, and then you just put the point. So if you look, like the figure 10 is basically about the same 8 as like the 001 in the figure 9. It's just that like it has been a bit rescaled, but yeah. Does this make sense?
A little
Is
bit,
the
yeah.
figure on this? Yeah. So you can encode stuff like in the angles of the gates. So when I say angles, like you remember the RY gate I made you put, right?
Yes.
And there was like some weird angle in that. And so this is what I mean when I say you can encode it into this angle. You can literally take put a bunch of, let's say, RY gates or RX gates, and then change the angle so that it gives you like the distribution that you want. There's a lot of research actually on how to do this properly so that you have the state that you want. And actually, depending on the hardware, it become a very interesting problem. So, anyways, you can encode it into the amplitude, as you can see, or you can encode it also in the way you measure it in the basis. There's different way to encode it, but yeah, this is something when I started, I did not understand like at all how you would even like get something useful into the quantum computer. And I think this is a cool example just to show that.
Yeah.
Let me see. So I have a bunch of, oh yeah. Oh, I just happened to open the LLM paper. Okay. That's actually lucky. Let me send it to you actually. So something I can tell you is that while the like quantum machine learning, everything machine learning related is not is dequantizable, and not all of it, but you get the same asymptotic and not improvement, but like you have the same complexity on both. Okay.
Wait, where'd you send it?
Or begin. Oh, I forgot to send it. Let me do it. So yeah. So in case, there you go. Yeah. So even though like in quantum machine learning you can have it's not clear if you have a like an advantage. The thing is that like even if the asymptotic complexity is the same, it might still take less step than a classical computer. And experimentally, I've run some quantum machine learning model where like it will take something like 1,000 step on a classical computer, but the quantum computer will do it in 5 step. Like the 5 step were really slow, but it will do it in 5 step only. And it's like theoretically like the asymptotic complexity is the same, yet you still have less step. So so there might be some benefits. It's just that we don't really know.
Okay.
So this is a high level one, a high level view on the LLM. So there's probably like a better paper. It's just this is the one I had in my all the cool papers in one place folder. So and so yeah, so okay. Comments? Any comments? Is there? I don't know. Where do we want to go from here? Do we want to continue? Is there some more question? How do we feel?
Confused.
Yeah, I did through. I threw a lot of stuff in one go, so there's a lot to take in. So it's quite understandable. So the thing is that do we want to go into the math right now? I don't know. Do we want to maybe research? Maybe we could look into like LLMs. Actually, I don't know. Like it's been a while since I've looked into quantum language models. So maybe I'll do a.
Yeah, I mean, I'm. So how would LLMs on quantum computer work?
Yeah, so unfortunately, it's not my specialized research. It's not like my main research topics. I have another friend though that like carried the whole project. I was not the one that like did the LLM for it, but like we could figure it out. It's not. And I think it could be fun. Maybe something we could do is like go through like not today, but like over time go through like an LLM paper, how they implemented it, and do it ourselves, something like that. What do you think of that?
That would be cool.
And then you can put all the buzzwords in your titles. Like you have machine learning, you have quantum, and then it's like VTuber, quantum, machine learning, LLMs. It's like crazy. Oh my god. Oh yeah. By the way, there's a lot of about that. There's a lot of people doing fake stuff in quantum computing. Like you'll hear about like some quantum blockchain stuff, and it's in quantum finance. It's like it's not quite a scam, but it's like I'm not sure about that. Oh yeah, something I wanted to show you also is that I think is very interesting is like this. There's this DARPA study currently that like there's this quantum benchmark initiative started by DARPA, and what they're trying to do is just know, okay, will we get actually a useful quantum computer? And so let me get I think it's this link. Okay, let me send it to you.
Wait, so in
There's
theory,
this
you
very
could
interesting.
run a
Yep.
blockchain. Sorry. So in theory, you could run a blockchain on a quantum computer.
So you can do stuff with blockchain with quantum computers. I'm not sure if you could realistically run a blockchain on a quantum computer.
Could you
That would be my answer.
could you quote unquote mine?
So
Like, you know how
actually,
people
there's
mine
people.
Bitcoin and stuff like that?
So there's people trying to do. I think it's called hash attack with the quantum computers. The thing is, there are people actually studying this. If you could do that, but the answer is if it's possible. Well, we don't know it yet. It's like very recent. Like a lot of paper I sent you actually is like from 2024 onward. And so maybe some guy will figure out a way to like mine Bitcoin with like quantum computers, but right now you cannot really. There's no algorithm really to do that.
Yeah, yeah. Damn.
Dang it! I know. If only maybe that would be the way to like make a bit of money, you know. So if you go on the link I just sent you,
Yep.
and you go on the fourth page, you'll see a very, very interesting graph. So I don't know if we say graph or plot actually in English. Like I always get these two terms confused.
I
Do
think
you
this would
know?
be a
Like
graph.
it should a graph. Okay. What's the difference between this and a plot? In a plot?
I'm not too sure.
Okay, that's fine. That's fine. So what's my research specialty? So right now, my research. So there's different field I want to explore, but right now my specialty is dequantization. So taking quantum system and trying to make them work on classical computer. There's also other stuff that I want to do, but right now this is really the main stuff I have the most competence in. So actually, this is why I have like some weird tricks where I'm like, oh yeah, I can simulate a 200 qubit circuit on my laptop, which is true, but like it always blow some physicists' mind. Well, the way to do it basically is using tensor networks and very specific circuit. This sentence is important. You need very specific circuit to be able to simulate like a 200 qubit system. Anyways, back to the DARPA thing. So basically, they're trying to figure out like when will quantum computer be useful, if ever. And they've put a lot of time into figuring out like what will be like the first application. So on the x-axis is basically the number of qubits, and the y-axis is like they say the number of operation. But if you listen to their talk, what they really mean is the number of T gates. But you could see it as like it's a bit like the frequency on your CPU or something like that. But it's like some weird DARPA metric or something. And if you look into it, something you see is that like there's a lot of quantum simulation stuff happening in there that would be really useful really soon. When you hear about breaking all the encryption in the world with the Shor algorithm with RSA, you can see that like it's the red rotated square. I forgot the word in English. It is what it is. Diamond. Thank you. So it's the red diamond there, and you can see that like it's right there. The funny thing is that there's also stuff like quantum finance, but it's so far up this graph that you just cannot see it. It just it's something like even if we had the best quantum computer with no error and anything, it will still take some trillion of years with the current quantum algorithm to do anything useful.
Oh, wow.
But there's other field where like in quantum simulation, quantum computer are really good at simulating quantum. So there's something called these Hamiltonian, and like I evolve like is finding the ground state of these Hamiltonian is actually something that is very that quantum computer are good for. And the problem that you see on the right is basically not all of them, I think. So I don't know everything about this. So obviously, like there's a lot in this field, but my impression is that like most of them are actually Hamiltonian simulation problem, except for RSA, which is like some crazy stuff that like some people in some some mathematician figured out. A bunch of mathematicians figured out that you could do. It's like the fact that we have Shor as algorithm, honestly, is kind of mind blowing because it's quite it's a really hard algorithm to understand compared to a bunch of other stuff in quantum. So maybe something I want to say is that like a word that you'll hear a lot is the word Hamiltonian. So let me just say what is Hamiltonian. So in Canada, in Toronto, there's this city called Hamilton. And so an Hamiltonian is just someone living in the Hamilton suburb, and that's it. I lied. So basically, so it's not people living in Hamilton. It's basically the energy of your system. So maybe if you remember, I don't know how much physics you have done, but maybe you have seen this equation, something like that. There's like some coefficient or whatever, but so you have like the potential energy plus the kinetic energy. I think it's it's like I know it in French, but in English I'll write kinetic. Maybe it's not the right way in English. So and the idea is have you seen like this kind of equation of like kinetic and potential energy before?
I think so, yeah.
So just a quick reminder. Here we will say that like if you were to roll this ball, let's do. If you were to roll this ball, like right now it has a lot of like potential energy. So let's say U is high, but it doesn't have much kinetic energy. And then when it reach the bottom, then your energy of your system would basically be at its lowest state that it could be. And so this is in classical physics. When you go into the quantum world, we represent these energy system with like something we call an Hamiltonian. So each time you hear about an Hamiltonian, it's really just like potential energy, kinetic energy, but like in the quantum realm. Does that make sense?
Yes.
So, yeah, okay. So when we go to the DARPA study, when I talk about like Hamiltonian stuff, Hamiltonian simulation, I have too many tabs open. Sorry. I need to close some stuff because I cannot find myself. Okay, let me do this. Okay, like this. I think it was this one. Oh, it's because it's, okay, I had a lot of, okay, I have a lot of tab open, but also I have 3 browser open. It doesn't help. So.
Oh my word.
Okay.
How is your computer not screaming at you?
True. Actually, it does. Sometimes while doing this kind of thing, sometimes my computer can crash because I run out of RAM. It's yeah, it's rough times. Also, RAM. Recently, I wanted to buy more RAM to fix that issue, but like the RAM prices are so crazy high right now.
Oh, you can just install
because
RAM.
of
Just
what they're doing with Elon.
And just
that's right. I forgot. Let me do that right now. Actually, how did I not think of that? Let me download more RAM right now. Okay.
There's an actual.
Should I do 4 gigabyte or 16 gigabyte? I think I'll take 32. I'll take 32. Okay. Downloading right now. Okay. Thank you. I had completely forgotten about that. Okay. This should fix all my issue. Oh my god. I should ask help from fellow VTuber more often. Holy. Download complete. Everything is done. Hell yeah. Okay. Problem solved. Okay. So yeah. So I think this plot is like one of the most is actually I think one of the most insane thing that like has been done so far in my opinion, because it's like nobody really knew what it will take to have useful quantum computer and how far ahead the quantum computer hardware must be for it to be useful. And then DARPA like launched this initiative, and now we finally have some idea of like how many qubits and how many operation you need to do to be able to do what you want to do. So and yeah, so 10 to the 2. So this means that like with just about 100 perfect qubit, you could already begin to do useful stuff with like I guess here it's dynamic of magnetic material, so it will be like some weird quantum phenomena. So yeah, that's another fun thing with quantum computing, is that it's really like classical computing where you can learn how to program it, but then you need to know another field to apply it to something. So there's a lot of field. You can apply quantum to quantum, or quantum to rendering, and quantum to like quantum signal or whatever. So it's like you can do quantum squared, or you can do quantum not squared. You can do even quantum cube. What I mean by that is that like sometimes you have like some weird math quantum problem that rely on like some weird quantum chemistry problem, and then you have to code it on like the quantum computer. It's like, okay, like there's a point where it's like, is it even humanly possible to know enough to solve a problem with a quantum computer? Like there's some problem that when you see, you're like, what is that? Okay, anyways, Okay. Um, okay. So where do we want to go from there? Are you fine? Is everything okay right now?
Yeah, no,
By the way?
everything's fine.
Oh, okay.
I have all the time in the world.
Um, oh, okay. Okay. So we can. Okay. So I don't have all the time of the world, but I do
No.
have. I still have more time. So we can do go into other stuff. Um, so yeah, if I don't want like to get in trouble, I won't show you. Like it's all public, but like okay, there's this very interesting field of quantum sensing, and there's like like maybe you have heard that like all the USA military is like 20 years ahead right now. All the military stuff that is happening in the future is in quantum sensing. So it's like it's probably not a good subject to touch on stream actually. Um,
Yeah, probably not.
uh, yep. Um, Oh yeah, so maybe I'll talk a little bit because I don't know if you knew, but there's actually quantum hackathons. Like just like you have like a CTF or like a classical competition where cybersecurity competition, you also have this kind of thing in the quantum world. So I've actually won a couple of prizes, and actually when Kran texted me, I was at MIT doing some competition, and we actually won third place there. So
Oh
that was
wow.
good. But see, that you might want to know is like, what do we do actually in this competition? This is like first the first question is like, what there's even quantum competition. Like, what does that even mean? Quantum hackathons, and then what do you do in that? So I'm just pulling up like a bunch of link that I think I'll have to send you. So I guess so we don't need to go into the details of it all, but da, da, da. This this one is fine. Tensor. Okay, let's go with this one. Okay, so I'll just begin sending you. I'll make a new zone called hackathons. And so yeah, so the thing to know is that like I'm much more on the computing side of thing than the physics side of thing.
Yeah,
Um,
yeah.
and so like to me the physicists what they're doing is still very crazy. Um, so let's go into Frontal Forest. So this is an example of like the kind of issue that you can be asked to solve. So it's a bit like you have like this kind of lead code type of challenge, and you also have like more of these project type of challenge. So in this case, it's like you have some oracle, and you need to be able to make an oracle such that it does what the problem wants you to do. And this is one of the harder problems that they give you, but it's just to give you a little bit of an idea. Like I don't know if you want to read this like or not. Yeah, we'll go into the next one. Another one is that like sometimes you have like these more physics based problem. Um, this
That's
is like solving differential equation, and basically your goal is to solve some differential equation in some weird way. So this happened in like ETH Zurich competition. There's also stuff like this is okay. This is such a classic one. Then you have stuff like okay, implement a paper, implement this paper. Like they just give you a paper, and they're like, okay, just do it within like 62. Is that wait? How do you say that? 70. Wait. Oh my god. How to? Okay.
72.
72. Yeah. Okay. Yeah. Yeah. So Yeah, 72. The thing is that like I never really studied my numbers when I was young on English, and because of this, I still have struggled with my numbers in English to this day. It's kind of crazy. So anyone listening to this, don't skip your numbers when you learn a language, otherwise, like you're cooked. Okay, so in this paper, yeah, basically there's something called QAOA. The idea is that like let's go into so the idea is that like you have like two type of circuit. You have a mixing layer, and then you have like your evolution layer. Let me just Google just really quickly because it's not just evolution. It, yeah, there's a bunch of library also, but like if you wanted to get started, Penny Lane is probably a good place. It just I just want to remember, yeah, the cost Hamiltonian. It's just the cost Hamiltonian. So it's like you, yeah. So U is fine. U is fine here. So the idea here is that like you have some you have like some quantum circuit. So this is an abstraction of the gates that we've seen earlier. So earlier I was showing like individual gates. This is a cluster of gate.
Okay.
Both of these are cluster of gates. It's just that like we don't write everything because otherwise it will take forever to like, you know, like talk about what you want to talk about. And so
Yeah.
QAOA, the way it generally works is that like you have some data that you have some data, and what you do is that you encode your problem in like some smart way to find. Like you encode your problem such that you have a cost function that when you minimize, you get the result. So in simpler words, you create a cost Hamiltonian, you encode and you just encode it into your circuit, and you optimize that cost Hamiltonian with some ansatz. Oh my god, what's an ansatz? Okay. Oh my god, how can I say this simply? I don't think there's a way to say it simply. There is for sure, but okay, there's some algorithm that like vary the angles of gates,
Yeah.
and the goal is that you want to measure an expectation value. This is like a statistical mathematical object, and you want to minimize that expectation value. So I'll just say like here I'll measure, and then you get an expectation value, and this is a value that can go like from like minus infinity to infinity or whatever. No, what am I doing? And what you do is that you have like some machine learning algorithm that look at this expectation value, and this is the basically this act as your cost function. So in this kind of circuit, the thing to remember is that you have like a classical layer. So basically, you take the input, you go into a classical computer, yeah. Then you prepare the state back to the quantum computer. So you prepare your circuit with certain angles. You measure your circuit depending on the result of your measurement. You decide which angle to change with like some machine learning optimizer, and then you run the loop again until you get like the angle that you want. That gives you the smallest energy or the smallest expectation value. Like the cost function gives you some. So basically, your quantum circuit act as a cost function in a machine learning system. I don't know how much you got of that, but this is the kind of stuff that we do in competition quite often.
I got a little bit of that, but That is crazy.
Yes. And the thing is that like there's a lot of like mathematical background on why this somewhat work, but for this algorithm that I just described specifically, we actually don't know if it will outperform classical algorithm or not. And the thing is that we need such a big data set and such a big number of qubits to be able to test it out that we just don't know yet right now. And so if you wanted to like better understand this on your own, oops, there's this tutorial from Penny Lane. QAOA. Penny Lane. So yeah, the thing is that like everything, it might be scary at the beginning, but actually like I don't know how much you're familiar with like the pi notation or whatever, but like this is something I could actually show you right now. But yeah. Let's see.
Not too much.
So yeah, okay, so we can go through that maybe either later today or we'll see. Let's finish just the competition hackathon stuff. So like the QAOA stuff is like pretty well known. So sometimes what they'll do is that they'll be like, okay, here's like some here's some way to encode your QAOA problem. But now what we want to do is we want to be able to execute it on like some GPU. So you need to cut your quantum circuit in smart ways such that you compute something useful, but you can actually run it on a classical computer. So let's say I'll just do like an example. Like from the paper, it's like, let's say you have like nodes like this, and maybe they're all these. Each of these nodes are like data points for your QAOA problem. But you can also use each data point needs some number of qubits. So maybe something you can do is like cluster this data point and cluster this data point, and then do some smarting between them so that you have so that when you encode your circuit into a quantum computer, you can get a useful result back. So this is the example of stuff you would do during a hackathon. Like how do you? This is called circuit cutting, by the way.
Okay.
So there's way to cut your quantum circuit so that it's more manageable to do on a quantum computer, and then you can recombine the result together. Just that you lose a lot of precision doing that, but like yeah. So this is the kind of stuff we can do in hackathons. Other stuff is like sometimes you just have like like the traveling salesman problem. So let's say you're an Amazon driver and you want to know which house I should go first to deliver my package or what the package. You want to find the optimal route to and which house to go to, so that you minimize the time it takes you to do your job. Amazon has like crazy advanced algorithm to be able to do that. This is a really hard computational problem, but quantum computer can help with that. It's just that like we don't have like the quantum computer right now are not good enough to be able to like really help with this. A funny fact also is yeah, this is the okay. So maybe this is good. This is good. The dog price stuff is. I feel like I'm speaking a lot. Actually, I feel like I'm stun locking you in some sense.
Give me
is everything?
2
Are we good?
I have a bug zapper
Sure.
in my room and it's going off like crazy.
That's fine. That's fine. Yes, and that is where you impose some educated guess of what function describe your problem. So in the case of quantum computing, and then that is really just you make some quantum circuit that you think contain the solution to your problem. So you might put like a bunch of like RX gate or a bunch of like C0 gates and maybe a bit of T gates, and then you just tune these angles, and then that's like your ansatz. You just like created a quantum circuit with some angle that like you think contain the solution to your problem. So that will be an ansatz. And you can see that as like a quantum circuit as a function. So
Interesting.
so yeah, I was answering a Kran question. All right. So how are we feeling?
Like my brain
So
is
we
about
have
to explode.
not done like concrete math yet, but maybe we can make it explode just a little bit more, you know. So okay, so hopefully I gave you like a little bit of sense on like what you can do with quantum computer. Actually, there's a lot of stuff I told you that like I don't think I've heard anyone on YouTube mention. Like I don't think you can find video of like people doing quantum LLMs like in an interesting way, or like just people presenting technology that you can do, or like 3D graphics or that kind of stuff. So I think it's cool to just show people that like, yeah, you can actually do not quite useless stuff, but kind of cool stuff that are kind of useless in quantum computing. And actually, there's a lot of low-hanging fruit in this area because a lot of people in that field actually are interested in solving like, I don't know, like solving world hunger or something, not like how to do a cat on a quantum computer. But I don't know, maybe there's like some weird stuff that like if there were people going into like this more creative way of using a quantum computer, maybe some people will come up with like a really smart way to use it that like could then impact more serious subjects. So
Yeah.
you never know with research. So okay, so let's go with I guess I'll just do like a text field in. So oh my god, it's so small. Okay, let me do I'll make it bigger soon. I guess there's Quiskit. Then what else? There's a circ. We'll just do this for now. So these are like among the best, not among the best, but like the most commonly. Oh my god. Oh, okay, I cannot make it much bigger than that. Let's say quantum computing frameworks. So actually, if you want to learn about quantum computing, a good way is like these libraries are good to go. A bit honestly, Quiskit like they change their API every 6 months or something because it's like some planned obsolescence thing they have. It's like it's not fun. So like you make your code for your research project, and then if it takes you more than 6 months, it might not work by the end of it. It's like okay.
Damn. That would suck.
These darn researcher. Yep. And it really does suck also. Something I like to do is that if anybody is interested, actually, there's this codebook from Penny Lane. So if you open the codebook map, something you'll see is that you have like a bunch of nodes, but one of them is like Penny Lane fundamentals. It walks you through how to use their framework, and then you can go through each of their node, like the introduction to quantum computing, single qubit gate, multi-qubit gate, and that thing. And this actually is if you go through this and then understand the exercises, this is actually like quantum computing classes that you will get at a university. Like this, like there's some serious stuff in there.
Wow.
Like in my there's like an introduction to quantum computing in my university, and like it doesn't go as far as these tutorial actually. Like we just don't have the time. Like you can spend like a year on this if you wanted. So. Or less. I mean, it depends on your motivation, honestly. But But yeah, so this is usually like a good starting point for this. But like what I think would be cool in your case is we probably want to look into like the latest quantum LLMs thing that happened, and then we can look into the math of like what is required for that, and then I can just show you like the minimal amount of math that you will need to be able to do the project. Does
Yeah.
that sound good?
Yeah, no, that sounds good.
All right. Um, so I've noticed this before, and I didn't know you were interested into quantum LLM. So I'll search that right now. Also, I guess I'll.
So while you do that, you mentioned before that running an LLM on a quantum computer was slower but required less steps than a normal computer.
Um, so it was not for LLM specifically, but yes, basically for quantum machine learning, you can have these cases where it might take 5 steps, but it might take 3 minutes to do these 5 steps, for example.
Okay.
And that's just like an issue of like the latency between the quantum computer, like you sending command to the quantum computer and receiving it, the quantum computer having to prepare the state and like run the circuit and then sample it multiple times. And then you get the result back. And the thing is that like it's like it can run maybe 5,000 circuit per second. So it's like it takes less step. It might take less step, but because like the hardware is not quite there yet, it's like it's just comically way slower in every aspect right now. There's right now the only thing that like might be useful is really Hamiltonian simulation, like in on today's hardware.
Okay.
Um, so let's see what this gives me.
All right. While you do that, do you mind if I go to the bathroom real quick?
Oh, that's fine. That's fine.
All right. I'll be back in about 2 minutes.
Should I eat my cat? Okay. Okay.
Okay, I'm back.
All right. So yeah, okay. So by the way, like doing an LLM is not something that we'll do like in like one shot in an afternoon. Just so that we're clear.
Yeah, yeah,
Um,
yeah.
the timeline might be more within like if we want to do something somewhat useful with the time I have, it will be like within a year or something. So
Within a year.
yeah, I don't have like a lot of time that I can put into this, so it will be like, I don't know, maybe. Yeah, I mean
Yeah, no,
it's.
that's
I mean I can. Okay, so the thing is, yeah, is that too long, or is that too short for you?
no. That's fine. That's a lot of time. That's fine though. But that's
Yeah,
crazy.
the thing is that like maybe the thing is that like I cannot do this like every week. If I could do this every week, like it would be insane. But like it might be more like every 1.5 month or something. Um, but the thing is that like something I can do though is like if I can show you just enough quantum computing, maybe you're interested enough to do it on your own, and then like it could be done way faster. Um, so uh, yeah, just that I'm looking at this and is okay. So I think like if I was on this full time it will take me probably a week or two to do. Um, like from scratch. Another thing is that this is assuming that we do it from scratch in its entirety. Another thing that could be done is like there's probably some code that we can take online and just like plug stuff in and get the stuff out, you know?
Yeah.
So it depends on how deep you want to go, I guess. Let's see. Does this have a GitHub? It does.
Quantum AI VTuber. You know
Oh.
what? I'll be better than Euro then. That would be
It sounds
crazy.
great, you know?
The other problem is it would be
Okay,
a
so
lot
there's
slower.
apparently yep. But like you know, it's a year is actually not that much. So um, also, if we take or if you take like a repo like this um, and just work through it, like you could claim that you have like a quantum LLM running or something. So I'm not sure exactly how we will have to spend some time into figuring out like how do we even use this thing. But yeah, so there's a binary accuracy. But yeah, yeah. So I think the more realistic path with the time I have is probably just send you to like some open source like repo that already implement a quantum LLM, and then you just tune it somehow. Like you will have to figure this part by yourself, but like you probably could do it with like LLM everything now. It's like much easier. So
Yeah, no, that's fine.
then I guess there is this paper. Let's see.
Dang.
Do they have it? Um, so maybe something we could do today is just so I'm not sure how much you'll need to know to be able to do it with like if you just search for like quantum LLMs. Um, I'm not sure how much you'll need to know about quantum, but um, you'll definitely need to know eventually about summation. So maybe we could do like a quick course on summation right now if you want.
Yeah, we can do that.
All right. So I'll look into what quantum AI V2.
Can I just say I know that you know what you're
Okay.
doing, but it is now solidified that I now know what you're doing because you've somehow the way that you writ everything is mind-boggling.
Is my writing that bad? Come on.
No.
Come on.
One, it looks like a
I'm
doctor's
kidding. I'm
handwriting.
kidding. I'm kidding.
Two, it just like goes straight down, chucks a right, goes down, chucks a right again, and then goes straight back down.
True. True. I'm not sure what that is. Um, and then we're gonna go left now. So, all right. So let's go. So I've been doing something called the Math Academy recently, so because like the thing is that I come from a CS background, but like it's not like we see it's not the most math intensive degree you could do in your life. And the thing is that I end up working with like physicists and mathematicians, and like their math skills are like at the PhD level, it's much higher. And so there's this platform called Math Academy #ad, I guess, that like basically use something called the like it use really to I don't want to spend too much time on this. So it use really smart algorithm and like smart cognitive science stuff to make it so that you learn math extremely fast. And the thing is that it's a bit like Khan Academy, the free version. Khan Academy is totally free.
Yeah.
But it's just that like I find it's like I find it much better than Khan Academy, and also it actually has university level math courses, which I need because I've never done like abstract algebra or whatever in
Yeah.
my engineering degree. So Math Academy like helped me do that. And the thing is that I guess I'm saying this because like I've been writing in some weird way using affine because of in part because of Math Academy. Because I'm just taking a lot of notes, and then it's like, oh, I need like some weird space. I don't know. I don't know how to say it, but yeah. Anyways, summation. So I think so this will probably be the last thing we'll do today.
Yep.
I think we covered a lot of stuff. So, but like summation is really important, and yeah. So let's go with this. Okay. So you see my cursor? Do you see it?
Yes.
Okay. Okay. So this is a summation. So we'll do something really simple. And so let's say that I'll replace this actually with like 4. So this equal 1, 2, 3, 4. Not so bad. Let's do this 2 with E here. This is equal to 2, 3, 4. Now what we're going to do is that we're going to do the same thing, but this time I'll ask you what this is equal to. So this is called a sigma symbol. All it does is it sums your term. It's like a for loop in programmation, but it's like the mathematical way of doing it. So now is the time you need to ask me a question. You need to try it or something. If there's something you don't understand, you ask it, and we go from there.
Okay, would that be 3, 4, 5?
Here, no, it will not be. No, it will not be 3, 4, 5. You can write, by the way.
Wait, how? What? Plus 1, 2, 3. And that's plus 2.
So maybe something I should say is that like this is the starting index. Oh,
Math is never my strong suit.
and this is like the ending and index. We'll just do this, and I think I'll have like sufficiently blew your mind for the day.
Well, now we're getting into
Maybe
the
it's
part.
already too much. Yeah, now it's actually like I wanted to do a little bit of math at least, just like just to have some progress. Okay, the thing is that like you don't need to actually like know all the smart tricks on how to compute this, but you do need to know what it does to read some of these paper. But like the thing is that like if you just take code from online, maybe you don't need to do that. But like eventually, maybe in 2 years or something, you'll want to really make your AI crazy smart, and then you'll need to dive deeper, and then you'll need to know that. So
Yeah.
so here, for example, we start at 1, then we replace the I with the 1, then we put it there. Then what we do is that we put the plus sign and we increment the I. So now I is equal to 2. We put the I here, and then we put it here. And then we continue. So now E is equal to 2. So now we increment it. It's now equal to 3. We put it here. So 3, E equal 3. So it's just 3. And so on. So are you able to write here what this sum should be? Putting you on the spot, huh?
Okay. Well, hold on. Go back to this. So how, if I equals 1, right? That's
Yes.
this part right here, right?
Yes.
Then how does where does I then equal 2?
So I start at 1. This is like the starting index. So I equal 1. So this is as if you replace the I by 1, and then it's like just like a for loop. So you go from here to here. You insert the I that's there into here.
Yeah.
And then you increment it, and you check, did I reach this value? This is my I greater than 4? In this case, no. So what you do is now you go back and you're like, okay, I equal 2. And then you go here, you substitute I by 2. And then you look, is my 4 is really bad. my bad. Is my 4 is 2 greater than 4? No. So you continue and you're like, okay, let's move all of this a bit down. There, this is cursed. I'll just delete it. We don't need it. And then it's like, is this 4? No. So we continue. So now we have E equal 3. So now what we do is we substitute it into this, and then it's like, okay, is 3 greater than 4? No. So we continue. So now we have 4. We substitute it again, and then we put each time we finish a loop, we put a plus sign, and then so on. And now we'll have like, okay, so the way I did it was like a weird analogy, but like you would actually stop at 4 because it equals 4. So, or in programmation, it will be something like 4 int E equals 0.
So then your answer here would just be 4.
My answer here will be 1 plus 2 plus 3 plus 4.
No, over here.
Oh, here. Oh, here. No, it will be 1 plus 4 plus 9 plus 16.
But isn't it above the 4?
So you have this index, but this index will go from 1 to 4, right? So this is fine. Okay. So far, so good. But what you do is that you substitute this index into this equation. So it
Okay.
will be 1 squared plus 2 squared plus 3 squared plus 4 squared. Does that make sense? We can do another one. We can do another one.
Okay, yes, please.
All right, let's do 3, and let's call it k this time. Let's
Now
say
I think I know what.
let's just say k equals 0. Let's do 1 plus k. What is this equal to?
One to K. Would that be 1 plus K, then 2 plus K?
It will be 1 plus 0, and then 1 plus 1.
How? What?
So the
Why?
k, you substitute the k by the current index. So here, this is the current index. Well, this is the starting index. Let's not be confusing. This is the starting index. And then this, you substitute the index into the equation. And then you increment the index. And then you sum. You add a plus sign. So I'll do another example like on the left just to really make this stick. Let's say I did something like this. So the sum of that would be 3 plus 6. This is 18. So on the left side, you have an example on how I would solve it for k plus 3. So something to know is that like the k will go from 0 to 3. And between each iteration, you sum them. You put the plus sign. I feel like I'm confusing.
I was just never good at math.
Oh, don't worry, don't worry. It's acquirable. You can acquire it. I swear. You'll be fine. Like just a little bit of math here and there. Eventually, like you'll be like a god in math. You know? Okay. Well, maybe not a god, but like like be able to do stuff at least. You know. Um, um, all right. So, well. Do you want to try again, or what are we thinking?
We can go again.
Okay. Let's let's go to the let's go here. Okay, a little bit more here. Um,
Great heavens. Math is hard. Math is hard.
So let's go for k equal 1. And I guess I'll just do k. What is this equal to?
Okay, that's the same as this one. Just
Yes.
Yeah, would that not be the same output?
Yep. Write it up, just to be clear, but without looking at the output of the other.
Oh.
It seems silly to rewrite it, but like it actually helped the mind. So
Are you red now?
wait, is it like not working properly?
No, you've
Okay.
just changed color.
But sorry, what? I did not catch that. Sorry.
Your cursor changed color. It was green before.
Oh, yeah. It's because I closed my app and reopened it. There was some bug, so. Yeah, so this will be a plus, but yeah, hell yeah, you got it, easy, first try. Let's go on
Definitely
to
first try.
definitely first try. Let's go k equals 0, and let's do it again with this. What is this equal to?
Ah, great heavens!
I believe in you.
You wouldn't
Praying.
start
I'm
at one.
praying.
You wouldn't start at 0, would you?
I would
It pretty
start
much
at
was the
0.
same, but you'd start at 0.
Yes, exactly.
Don't mind my atrocious handwriting.
Yeah, that's fine. It took me a while to be able to write something that was not an utter disaster on Affine, so. All right. So this is good. This is excellent. This is like, holy shit. You're on your way to become like a mad god. You have no idea. Now, the challenging one. Let's do k equal 2. Then let's put, we'll put 4. And then let's do k plus 2.
Oh, great.
What is this equal to?
That would be. Something like that. But then you give.
No, not quite.
6,
So
8.
on the right side, the k should be substituted with the
62.
current k value.
62.
Yeah. So no, substitute.
Oh, okay.
Yeah, maybe I mispronounced it. My bad.
It's like, wait, what?
So yeah, you need to substitute k with the
Okay, so
current
that-
k value.
That would be 2, and that would be 2, and that would go up to. 6. To 6, 8.
Okay, so this works, but accidentally. We'll do a final one. K equal 2 to 4, but then we'll do this. What is this equal to?
Sorry, then how? Wait, how was that accidental?
It's
As in you
math-
told me the answer,
like-
or
It's accidental because you'll get the good answer for this one, But the way you substituted the variable is not right. Like it just happened that the way you did it will work for this one.
Oh, you do the two, the 4 and 2. So you'd pretty much just swap those around.
Yeah. Basically,
Okay.
yeah. And so the last one, just to be sure, I know it's annoying to do, but like that's how you learn. You need to like really go into it, go into the trenches, you know. So especially for maths. So can you do can you do this one for me, and then we'll be done.
Um, what is that?
That's k. That's just k. K squared.
K2, K squared. 4, 6, 4.
Yeah, 2 squared is 4.
2.
3 squared is 9.
Thank you.
And then
Wait,
the
well,
last one. Wait, yeah.
why would you go 3 squared if it's only 2 squared?
Ah, that's the when I say that the index increase, that's the part that you have to
Oh,
understand.
okay.
Because we started at 2, then we increase to 3, then we go to 4. Yep.
2, 4, 6. 4 2's 16.
Yes.
2 6's 32.
Yeah. So you can stop there because you already reach the 4th index actually. So it will be 4 plus 9 plus 16.
Oh, okay. So you don't need the 4 digits. You only need to get to that.
Yes, you only need to reach it. You don't need like you only need to go to 2, 3, and 4, but you don't need 4 element. You just need to reach 4. Does that make sense?
Okay. Yes. Yes.
All right. Yeah. Okay. Well.
Great heavens.
I think we'll stop here at least for the math part. I don't know if we'll do much more. Uh, any comments, insult or whatever?
Damn, I'm gonna have to go to math. Ew.
Damn right. Damn right. Um, but don't worry. Like honestly, like it's like school make you, I think school make everyone hate math. I think that there's fun to be had. In there somehow. At least that's what I've been told too. So. Um, all right. Well, I think I will end it for today. Would that be good?
Yeah, that's good. Before you go, Kimberly just said, how does this relate to quantum computing?
Yeah. So okay, maybe I'll do something really quickly for Kran, because I know Kran, like he can do scientific computing. So the thing is that like, so I'll go with a really quick explanation just for him.
Sorry, did you just say that? No mind. Continue. Sorry.
You what?
No, nothing.
Okay. No. Oh, well, I mean, no, but you know, we're all at different stage of life. You know, it's fine. It's good. We like that. But like, the thing is, the summation stuff, like the thing is that you can then translate the same logic into quantum computing. So let's say you have a Q0 and K equals 0 and 3. Something you could do is do something like, let's say, xk and zk. So what this will mean is that it's the same thing as doing xz, xz, and xz. So the thing is that, like, in the research paper, what they'll do is that they'll write it, this thing, this is a tensor product,
Yeah.
and they'll write it these and these paper, like they'll write this kind of notation that like is basically the summation, but like but like it's just a different symbol than the summation. So instead of doing pluses, you do x1 z1 tensor, x2 z2 tensor, x3 z3, and that's it. And this is equal to this. And the other thing that they'll do also is that, so have you seen? So as you see here, it's kind of alluded to this, but like a multiplication in quantum is actually just like 2 gates. So if I do, like, let's say x k, and then I do k equals 0 and 10, then what this really means is that it's the same thing as like this thing. I don't need this actually. 10 times. So a multiplication is like the same is like on the same qubit, and a tensor is like on 2 qubits. Okay, so 1, 2, 3, 4, 5. So I'll just copy that. So this is the extension of the idea, and why I'm presenting it to you is that like you'll actually see this kind of notation and this kind of notation quite often. It's just, if you're not familiar with the summation, it's like it's hell. You cannot. It's like hell. So that's why I prefer showing notation first.
Yeah.
Yeah, with the summation. So, so I think this answers your question now, Kren. Are you happy with that? I'll take the silence for a yes.
So multiplication can be done with qubits. Qubits?
Yeah,
In
qubits.
series, tensor with parallel.
Yes. So tensor product is basically like parallel. It's basically on multiple qubits. So it's a way to say it. Yeah. And it's just that like mathematicians love to be annoying with their notation, so they'll write it this way. But like you were able, and Lunako, I just want to tell you, you were able to understand what we were doing when I was showing you the IBM Composer stuff. Like, believe it or not, but you were doing quantum computing already. Like, it doesn't have to be like this math hell type of thing. The math hell only happen when you want to like create your own algorithm or something, because then you have to really understand what happened in your quantum computer. Also, like we could do a lesson on like what mathematically this represent, but like I feel like we've done a lot today, so yeah.
There. That's
Yep. So yep, your homework is due next week. I'll wait patiently. If you fail, you fail at life. If you fail the homework, you fail at life. It is what it is.
next.
That's how Quift University work. So
I would.
I don't give degrees. I just give accidental death threats. So I don't know. I'm not kidding. anyways.
I find this very fascinating. But doing this as a career would would send me into early retirement.
Well, I do get crazy about it. Like there's time where it's like you have like these physicists that are like, oh, what if we need to improve the noise? What if we can solve the noise with the noise? And then you hear them talk. You're like, what are they saying? I'm getting crazy just hearing what they're talking about. And then they have some weird theory about like some weird elder space interacting in some weird way, and they're like, oh yeah, this will make it so that it works. And then they do all of this work, and basically all you have to do is like put an Hadamard gate, and you're like, what happened? Why are we here? Like, come on. Like it just like it can get really crazy, and you get like your brain get cooked sometime. So yeah, the physicist people, oh, they're crazy people, I tell you, and they make me crazy. Oh my god.
My brain.
So yeah, go ahead.
That would be insane. Damn.
And so something we could do, maybe if we do this again, if you're up for it, we could actually go deeper into like what it means to have these gates. Like what are the operation? How do you manipulate them? We could also go into the direct notation and go a bit more deeply into this. So you would actually be doing a little bit of physics technically, but like without having to understand all of the physics, without the cringe. I'll say it like that.
Okay. Yeah, no, I would be down to do this again.
Okay.
If like when you have time in it, if you want to do it again.
Oh yeah, I definitely want to do it again. It forces me also to like be sure that like I'm top notch on like my basics. So I like that. Yeah, we could do it again. It might be like maybe like more of a once per month thing.
Yeah, no, that's
once per week thing.
Yeah, no, that's fine. Whenever you have spare time or whatever.
That's good. Okay, so if it's one per month, like I definitely can manage like some time slot like today. So yeah, that's good. Holy shit, we did cover like quite a lot.
I feel like
Yeah. By the way, I did not prepare at all for like the constructing a computer from scratch part. So I'm glad I was able to do it on the go. So yeah. Okay.
this is my math done for the next month.
Yeah, I can feel that. Okay. But thank you. Also thank you for like taking this time. Also, I think it's kind of cool that like it's like it's really 2026. It feels very 2026 that like I can be like, oh, let's do quantum with a VTuber. I think that's hilarious. You know, it's like that's kind of like the whole reason I'm doing this is that it's like a great shit post in some sense. So I like that. I like that.
Me, there was some teachers at school that were talking about quantum computing and AI and stuff like that, and that's actually what originally sparked that. Imagine having an AI, quantum computing that can run violent, and then Canberra went to you, and yeah, that now I can go back to them, to the teachers, and be like, hey, I know what I'm doing now.
Damn right. Damn right. Okay, maybe wait until the next lesson, but like, damn right, you know. Like on the next lesson, I think you'll be quite impressed on how far you can go with like just a little, just like this kind of stuff that we're doing. So it doesn't like like just understanding the summation is already like, if you've never seen this before, it's actually quite good actually. Like also like so I think you have a better concept of like what you can somewhat do with a quantum computer, and I did not go with like all the like usually people talk about a lot of other stuff about what you can do with a quantum computer. They always talk with like this theoretical algorithm. They'll start with like I think it's Versitani. I cannot say the name. It's like some weird German name, and it's like you read these and you're like, what? Yeah, yeah, okay. You're like, oh, this is great to demonstrate like quantumness, I guess, but like you don't get what you can actually do with them. Hopefully, you get some sense that like yes, you can do some LLM, but you could also like do some. Technically, you could do some video games, and you can do that because you can encode stuff in some interesting way. Hopefully, you have like some vague idea on how you could encode stuff into a quantum computer, even though like you might not be able to do it directly technically, but like at least you know, like you will know how to ask ChatGPT to do it, I guess,
Yeah.
and that kind of stuff. So
I think that would be
yeah.
another pretty. Sorry, I need to let you go, but I think that's probably another cool thing. With the what are they? The no programs. The string of information or whatever it was, I can't remember the name of it. But like using AI to help create those different type of things. I hope that you know what I'm doing. I can't explain it.
Like using AI to like design a quantum circuit or stuff like that, right?
Yes. Or not necessarily like purely design it, but like help design it.
Yes.
Maybe.
The research that I'm doing, we end up like so. LLMs are actually quite bad at quantum right now. Like comically really bad. So, but
Oh
like
yeah, no, they are.
but like what they're great at is like all the classical optimization part. Like it's much more easier to do now now that you have like an LLM that can parse your data. You don't have to spend hours just understanding how to parse your data. An LLM can just do it. So, and there's a lot of stuff where it's like there's actually research going on where there's some photonic company that like they want to put some quantum circuit and then they're onto their quantum computer and then they want the like some LLM or some intelligence system to try to describe what happened in the quantum computer from the output directly and from the gate they said they've done. There's like really cool stuff happening right now with like machine learning in quantum, like in the application at the application level. So yeah.
Yeah, that's kind of cool. All right. Well, I shall let you go now. So
Yeah.
I'm not holding you on too long.
All right. So
Damn.
I think I'll go now. So
All right.
see ya.
Thanks for the chat today.
It was a pleasure. It was great talking to you.
That blew my mind.
Hell yeah, I like to hear that. All right, see ya.
I shall get in contact with you about the next one.
Yep.
All right.
I'll send you a DM. Yep.
Cool.
Yeah.
All right. Bye-bye. I don't know how to end off these things sometimes. I don't know how to end off these things sometimes, especially conversations. I don't know how to do it. Damn. I absolutely suck when it comes to the knowledge on that type of stuff. But dude, holy crap! I know I missed like a lot of chat, and you know I'm sorry about that, but damn, that is a lot. You know, if we end up like doing that, like going down the route where we create the LLM to run on the computer or whatever, dude, that would be kind of cool. That would be kind of cool. It would take some time. It would definitely take some time because I wanna get like what do you call it? I'm gonna get Violet done first before I take on another project. But holy damn, that again. Thank you, Canberra, for getting in contact with them for me. That was kind of cool. I am gonna go get some sleep because my brain has now exploded. Also, that comment about you being smart. I didn't realize that you were like that smart. Damn. He said something about that you knew something about it, and I was like, wait, hold up. Dang. Are you interested in it, Canberra, or are you like research? I don't want to dive like too deep with it, but like, damn. I'm gonna go tell my teachers now. But I don't know. That's kind of cool. All right, I shall catch you all in 2 days, because in 2 days we're gonna be streaming. Not today, not tomorrow, but tomorrow. Not tomorrow, but the following day we'll be streaming again. But yeah, with that being said, I shall catch you when I catch you. Enjoy.